Okay, good afternoon, everybody. I mentioned earlier, my name is Vince. I work at Flownex in South Africa. My work involves some development work as well as some high-level technical support. What I'd like to do today is to talk you through some tips and tricks on how to use Flownex effectively. Some things that I've picked up over the years that I've been using the software, and basically just to give you guys an inside look as to how we at Flownex use the software. Just before we get going, I'd like to just give a quick overview. First, just for anybody who's new to the software, I'd like to give a really quick introduction as to what Flownex is. Then I'd like to begin a discussion around what we think about before building a network. So actually before you start dragging and dropping components, what are we thinking about? What are the important things to consider? Next, I'm going to be looking at some user input tips, things that you can actually do inside of the software, hotkeys, little shortcuts, things that can just save you time. The next thing I want to talk about, sort of leading on from what we think about before building a network, is some tips for working on large networks. A couple things just to keep in mind, and yeah, some good practices for those applications. Next, I want to talk about the components that we use most often. So discuss which components we find as more general use components and why we prefer certain components over others in certain situations. For new users, it can be a short list of components that are very helpful, components that do a lot with very few inputs. And for more advanced users, it can be a good guide as to why we would use one component over another in a certain situation. And then lastly, I'd like to talk briefly about time step and increment selection inside of Flownex. Often increments are just a number on the pipe component. I want to talk about when this input really matters, and then when selecting time steps, what are good values to choose, and how do we go about refining our time steps? How can we be confident in our results? Okay, so to get started, just for anybody who's new to the software, Flownex is a one-dimensional system simulation software package. We use it for system analysis, so that could be design applications or operation applications, even maintenance, where you're looking at replacing components and understanding what effect this component being replaced will have on the system. The software itself is based around one-dimensional flow components and two-dimensional heat transfer components. This basically allows us to build a conjugate heat transfer network, simulating both the heat transfer and the fluid flow, and ultimately forming a full system solution. Flownex uses a CFD pressure correction method, or a CFD-based pressure correction method, for both steady state and for transient or dynamic analysis. The software also includes a couple of analysis features just to help the engineers out. We have a designer, optimizer, and sensitivity analysis function. This is basically just there to assist engineers in making automated changes to an input to achieve a particular result on another input. Perhaps you want to change a pipe diameter to achieve a particular velocity in a pipe, or you would like to change a heat exchanger length to maximize the output power of a particular cycle. So these analysis functions are there to just make this process a bit easier. Flownex itself includes a couple of different fluid types. We have fluids for liquids, for gases, and for two-phase fluids. But then we also have a couple of other fluids aimed at mixtures and more non-traditional fluids like settling slurries, for example. Lastly, Flownex itself is designed within an NQA1 and ISO 9001 environment. This basically, these are strict quality control standards which allow the software to be used in nuclear safety cases. So the software itself goes through a lot of procedures in terms of maintaining quality, ensuring that all of our work is verified and validated before the software is, or before a new release of the software is released. Okay, so to start today, what I want to do is talk about the thought process before working in Flownex. So in a typical scenario, an analysis exercise or analysis, a piece of work for analysis might start with a manager proposing a installation of a new system, or a design team leader proposing a modification to a system. And then as the engineers, they're going to be doing the analysis. We're trying to go from this high-level scenario with a new system development or a modification to an existing system, and we want to go from that goal into a simulation to get some answers to very particular questions, be it the size of components, or what will happen if this component fails, or is this system safe under these scenarios? And we want to get there as quick as possible. At the end of the day, we're all still working for businesses, so the time that we spend working on these simulations is incredibly valuable, and we need to make sure that we are as conscious of the time we spend and use it as efficiently as possible. So basically, we want to go from this business management style into successful engineer with a solution as quick as possible. And we want to try and avoid the deliberation, the obsessing over small details in the simulation. The engineer that spends so much time on the analysis that they lose track of what the actual design goals or what the analysis goals of the particular project were. So putting that a bit more into words, the first step that I would say we think about before building a network is formulating an engineering question. So to actually guide through this philosophy that I'd like to describe, I'd like to sort of frame it in the case of an example. So imagine that there is a pressure vessel with some material inside that needs to be washed with hot water or warm water. A chemical engineer has specified the requirements for this particular washing process in terms of temperature, in terms of pressure. And as a process engineer, as a system engineer, we need to design the system that can now facilitate this washing procedure. We want to have a pressurized vessel with the level in it, and then we want to have some spray nozzles at the top, which can allow this warm water to be sprayed over our material and ultimately wash it. So we're going to have a system with a tank, a valve to control the level inside of the tank. There's going to be a pump to recirculate the fluid so that we can spray it down onto the material. And we basically want to size some of the components in here. I'll show a diagram of the system in a second, but just visualize what the system could be. We're going to have a tank with a pipe leading out of it. There's a valve in line with that pipe. This pipe then leads into another tank. This tank is then the feed for a pump, which recirculates the water back into this original pressurized vessel. So in terms of the engineering questions we're trying to answer here, the system design really, or at least for this exercise, will focus around two aspects. What valve should we use? So what should be the CV of the valve? And also, what is the pressure rise required for this pump? These engineering questions are key to address early on because they really dictate the decisions we're going to make in the simulation process. The next thing that we need is some layout of the system. Often what will happen is engineers will be working in big plants, or somebody will describe a new system on a whiteboard, and we'll start building right away without actually considering the system in a bit more detail. Taking 10 minutes or so and drawing out the system, be it in a notebook or even in something like Visio. You can actually gain a lot of insight to the system, make sure that you understand the layout of all the components, and more importantly, include information you already know about the system. Known pressures, known temperatures, known flow rates, elevations inside of the system. Any information that's going to be critical at the simulation stage. So what we have here is a rough sketch of what the system might look like. We have the pressure vessel. Inside of this pressure vessel will be the material that needs to be washed. We're going to have some inlet at the top for our water recycle loop. That water is going to be fed from a pump, which draws its water from a waste bucket. Water then flows out of the pressure vessel and then into this waste bucket, but this water flow is then controlled by a valve in this line. So we have flow out of the pressure vessel into the waste bucket, and then from the waste bucket through a pump and back into the pressure vessel. This allows us to circulate the water. We then have another system on the left here, which has some compressed air and a pressure regulating valve, and we're using this to maintain the pressure inside of the vessel. So we're adding air to basically ensure that the liquid inside of that vessel is at its target pressure. For this hypothetical scenario, let's imagine that the pressure inside the vessel needs to be 2 bar, the water needs to be injected at say 50 degrees Celsius. We're looking for a flow rate of 10 cubic meters per hour, and we have an elevation difference between our pressure vessel where our material is stored and the waste bucket where the water will be temporarily stored before it is pumped back into the pressure vessel. What we have here is basically all the information we need to start our system, but we don't want to just jump straight in after this. We need to first analyze our drawing and start figuring out if the system here, if everything that we've drawn in our system is strictly necessary to answer the questions that we have. So the next line of thought that I'd like to propose is, what do we really need to simulate? Do we really need to model the entire system? Is it really necessary to model the air system on the left-hand side, this pressure regulation system? Is that going to have an effect on the size of the valve we choose or the size of the pump we choose? Are there any sections that we can model with boundary conditions instead? Are there any points in here where we don't really need the detail of what is controlling that pressure? We can actually just replace it with a pressure boundary. If we're designing for the steady state operation, then we can assume the control system that's trying to control this pressure, for example, is operating well. If it isn't operating well, we can simply vary our pressure boundary to simulate any miscontrol or any error in the control system. We don't really need to model the system in its full detail to analyze the effects of small changes. And then the next thing, which is really important, is can I build the network in parts? Dragging components in on a small system like this would be pretty straightforward. If we made a mistake on the inputs of any of these components, it wouldn't be the end of the world. We have maybe 10 components to go through and check our inputs. But imagine your network is much larger. You're modeling a turbine train inside of a large power station. And you're trying to figure out where the input mistake is on one of your components. The actual debugging procedure will be so much easier if you were able to build the network in portions and then solve the network, see if there are any errors, correct any of those errors, and then continue building from there. So basically correcting your mistakes before you go and repeat them. So if we take a look at the system, like I mentioned, the system on the left-hand side with the air, we could basically ignore that. This could be treated entirely as a pressure boundary condition on our pressure vessel. We say that the compressed air system is operating as designed and is maintaining the pressure at 2 bar. So any flow regarding the air on the side wouldn't really add any value to our simulation. The next thing is, if you look at the area inside the green box here, we could simulate that area and have a completely valid network or branch in a network with the relevant boundary conditions. We'd have a pressure boundary on our pressure vessel, we'd have a pressure boundary on our waste bucket, which would be exposed to atmosphere, and then we'd have all of the specifications for the components in between. So we'd have a valid network that we could solve at this point. We wouldn't need to model the pump and any of the piping at the top here in the recirculation loop before we could actually solve this network. So we could build half of it, test that our network solves, correct any mistakes in our inputs, and then after we've done that, move on to modeling the remainder of our network. So that's exactly what I'd like to do. I've got a blank Flownex project over here, and what I'd like to do is go through the steps that I would use in building that. So we have, jump back to here. So we have a pressure vessel with the pressure maintained on the surface at 2 bar. So the way in which I'd like to do that is use an open container. The name might sound a bit counterintuitive here, but what we're doing is applying using a container that has a free surface pressure input. This is useful when simulating something like a dam that's exposed to atmosphere, but it could very easily be used to simulate the liquid level inside of a pressurized container. If the air system is maintaining the pressure at the free surface, we have a component that is modeling that without the need to include the air in the system. So our specification here would be 2 bar. Small note, inside Flownex, we can actually type the unit straight after the number. So instead of typing, instead of changing the unit to bar and then adding the value, we can simply type the value and then add the unit afterwards in text, and Flownex will automatically adjust that unit. So it saves a bit of time if you're inputting a lot of information. This tank over here, we're going to just assume that the level inside the tank is maybe 1 meter. I'm going to assume that the tank has a diameter of about 1 meter. The geometry I'm choosing here is completely arbitrary. I'm just using this as an example to explain my thought procedure. So try not to focus too much on the numbers. Think of the philosophy behind it. We then have our pressurized vessel connected to a hand-operated valve, and then some control valve, and then our waste bucket. So let's put some stuff in there. So we have a hand-operated valve. For now, I'm just going to use one of the valves in the Miller library, or the Miller section of the valves library. Here we can find something like a ball valve. That would be pretty reasonable as for a hand-operated valve. One thing you might notice, once I connect a flow component to a tank, you'll see a couple extra inputs will appear. You'll see that the height input is now an option, so I'm just going to specify that. And then also there is a connection fraction. This describes where this component is connected in relation to this tank. Is it connected at the bottom? Is it connected halfway up? Is it at the top of the tank? This is important for calculating any pressure due to the level inside of the tank. What effect that will have on the pressure at the outlet or at the inlet to this component. So here I'm just going to choose a couple inputs. Once again, I'm using the unit inside of the input. As soon as I press enter afterwards, it will automatically change the unit to what I've typed in. You can do this for any of the units in Flownex. If you're wondering about what to choose, just look on the drop-down list. One thing I just must stress is that it is case sensitive. So if you are specifying a pressure in kilopascals, make sure that the K is lowercase, the P is uppercase, and the A is lowercase. If you don't specify it in that way, Flownex will not interpret it as the correct unit, and it'll give you an error. Okay, so we have a hand-operated valve. We need some kind of control valve. For that, I'm just going to use the ANSI control valve. I'll talk a bit later about the components that we use most often and when we would use one valve over another valve or one component over another component. So we have the valve. Let's add some piping. So I'm just going to use the standard pipe component. This pipe is going to deal with the elevation difference between our tank at the top, our pressure vessel, and the tank at the bottom, the waste vessel. So let's grab another container for that. Okay. So this container over here, I'm just going to make a little bit smaller. Instead of it being 1 meter level, I'm just going to say half a meter. Its free surface is 1 bar, and then its elevation is 0. Diameter, we can say 500 millimeters. It can be a smaller tank. This pipe would most likely be connected at the top of the tank, so I'm going to specify its height fraction as 1. That way, the liquid level inside here wouldn't have any influence on the flow rate through the system. Our valve position can be controlled independent of the level here. Okay, that should do it for that setup. One thing that I have forgotten is the elevation specification on this tank at the top. So if we go back to the diagram, this pressure vessel I've chosen to be at a 10 meter elevation. Think of it as a constraint inside the plant. There's an existing vessel that you want to use, but the other vessel that you're going to use is a different elevation. So I'm busy modeling that by just changing the elevation input. If you're ever unsure of this elevation, you can actually add these inputs as result layers. If you click on the results tab and click result layer setup, you can drag in elevation, for example. Let me just remove this one. Elevation, right click, add a result layer, and then drag and drop the elevation in here. You can convert that to generic, update it, and then see in a scalar plot through these colors what the elevation specification on the components are. So if you're modeling a large network where multiple components need to have elevation specifications, and you just want to do a quick glance at the network, almost like a sanity check, then I'd recommend looking at using the result layers. It can be very easy at visualizing some of your inputs. So I'm just going to turn that off. Okay, so we have a pressure boundary condition indirectly specified here because we've specified the free surface pressure. Adding a pressure boundary would be overkill. So we do, however, need to specify a temperature though. So I'm going to get a boundary condition, I'm going to attach it to the tank, and then I'm going to specify temperature. If you remember from earlier, 50 degrees Celsius is going to be that temperature. And then lastly, we need to specify a fluid. So over here, I'm just going to grab some water, and we should be good to go. Okay, so at this point, I'm relatively confident that I've input everything in my network, and as I say that, I've realized I haven't specified this valve. So we need a CV for our control valve. For now, I'm just going to choose 10, and then we should be able to solve our network from there. So let's solve steady state. Oh, okay. As I do this, I've gone and forgot that. So I'm just going to add, I've missed the inputs on these components. So it's myself trying to get ahead, perhaps rush a little bit. So in this scenario over here, I can quickly identify where my mistakes are. I've got my valve specified, but my pipe over here doesn't have any inputs. You'll notice that the arrows are directing me towards the diameter and length fields. So the elevation difference here is 10 meters. To be conservative, I'm going to use 12 meters of piping. Let's use the same diameter as what I used for the previous piping. Use a typical roughness for steel, and then I'm going to add some secondary losses. There'll be some bends in this piping, but I don't want to add bend components and stress too much about the exact pressure drop. What I'd prefer to do, especially in an initial sizing like this, is just add bends through secondary losses. So add a K factor. So you can specify, say, 2 bends, press OK, and then that secondary loss factor is assigned to the pipe component and will just be added to the pressure drop through that component. So we won't be able to see the pressure drop over the bend directly, but that pressure drop will still be taken into account in the total pressure drop through the system. All right, that should do it on that setup. So we solve again. Okay, the area diameter value. Okay, because this pipe component doesn't have a pipe upstream, it needs a diameter specification as well. So if I add that, solve again. Okay, now we have a solution that's at least the solver has completed. We still need to look at our results and just ensure that everything's specified correctly. But just in, what is this, 1, 2, 3, 4, 5 components, you can actually make a couple of small mistakes here and there. Imagine if I'd gone ahead and built an entire system after this. Tracing back to find these small mistakes might be incredibly time consuming. So making these small mistakes now doesn't cost very much time. But later on, if you've copied this component multiple times, or I don't know, you've added additional components in the system, and an incorrect specification on one component is actually creating a problem on another component, you could have a really hard time trying to track down where your mistake was. So I strongly recommend this procedure of building the network in sections, trying to find the smallest area that we can model, and then go ahead and model that, and then add some additional sections of the network afterwards. If we look at the results inside of the system, you're going to notice that there is no flow. This valve component here has an opening, which I need to specify as 1. And then we should have some flow rate results. If we look at the volume flow, we have 13 cubic meters per hour. So that's close to the target flow rate that I'm looking for, but not quite there. To actually get this valve sized correctly, what I need to do is vary the CV value until I get my total volume flow to 10 cubic meters an hour. So perhaps I choose 5 as my CV value. I get a volume flow of 6.87. So I know my solution lies somewhere in between there. So we can use the design feature. We just add a designer. What I recommend doing is just naming these. When you build large systems, you can end up with, say, 10, 20, maybe even more different designer configurations. So naming them really helps when it comes to making small changes to your system and rerunning the designer. Here we want to vary the CV value. We know that our limits are 5 and 10 from our small tests. And then we'd like to achieve a total volume flow of 10 cubic meters an hour. One thing just to keep in mind, please check the units over here. Because I changed my result to cubic meters per hour, this is also in cubic meters per hour, but occasionally I do forget and leave that on, say, cubic meters per second and specify a target value as if it was cubic meters per hour. So just pay attention here. This is going to save you a bit of trouble in the long run. Okay, that should be our designer specified. If we now go back, we can run that designer. This should vary the CV value until our total volume flow is 10. So now we can see our CV of about 7.27 is a ideal CV to use for this valve. Obviously, we're not going to get that exactly, but that's going to be our preliminary value before we start looking at some catalogs from manufacturers. All right, the next part of our system can then be the pump and then any piping that's going to be needed to get back to the pressure vessel. So we have another hand-operated valve. So let me just take this component and copy it, just paste it over here. When you copy and paste components, it will retain all of its inputs. So if you're using a pipe component that's very similar to a previous pipe, you might as well copy that. It's going to save you a bit of time in specifying its inputs. So we have a hand-operated valve. We're going to need a pump. In this case, I'm going to use the basic centrifugal pump. This component is very good at, or very good for when you're doing pump sizing applications. It doesn't require a pump curve, and we can fix the mass flow inside of the component, and it will design itself in terms of the head required and the volume flow required to achieve that particular mass flow. So this can be very handy for pump sizing applications. We're then going to need some piping. So when you're adding a pipe, you can actually press or just tap the shift key on your keyboard and it'll rotate the component. If you do this many times and Windows has sticky keys on, you're going to get a pop-up. I just recommend you quickly Google that and figure out how to turn sticky keys off. And then that should never bother you again. So let's put that over there. All right, now time to specify these components. So the pump itself, like I mentioned, we're going to use the pump to actually, this basic centrifugal pump to design the pump that we require. But one thing that we do need to input is the speed at its best efficiency point. The volume flow and head will be calculated. We're then going to fix the flow in this component. And for now, I'm just going to choose 3 kilograms a second. We're going to have to change this so that we can achieve our desired flow of 10 cubic meters an hour. But we'll do that in a moment. Next, we have our pipe. Same story. I'm going to specify 12 meters, user diameter of, say, 100 millimeters, roughness of 50 micrometers, and then let's just copy the secondary losses from here, and then we should be good. Okay, this system now should be able to solve a gain. So we have another solution. Now we can look at the volumetric flow through this part of the network. Here we have 10.917, so close to our target value, but not quite there. If you look at this at 3 kilograms, we're getting 10 cubic meters an hour. If we use 2 kilograms a second, we get 7 cubic meters an hour. So we know that our target value lies somewhere in between there. So let's use the designer again, add another configuration, this for the pump mass flow, and then let's drag in the relevant inputs. We want to vary the mass flow until we get a volume flow of 10 cubic meters an hour. I tested it manually and I found that the solution is going to lie somewhere between 2 and 3 kilograms a second. So we can run the designer and then it should have changed our mass flow until we get our target volumetric flow rate. Okay, so at this point over here, we have our pump set up. One important thing, if you're using this component to design, I'd recommend you just change the option to change design. What that does is it will change the head and volume flow inputs to the head and volume flow inputs that are required to actually perform identically as if this component had a fixed mass flow in it. So it'll basically add the required amount of head to overcome the pressure drop in the rest of the branch, and then it'll specify a volumetric flow rate that would be equal to the mass flow that you've just specified. So if you remember from earlier, we tried to design for 10 cubic meters an hour, and as a result, our best efficiency point is also at 10 cubic meters an hour. If we now remove the mass flow specification and solve, this component is now going to use this best efficiency point and vary the performance of the pump in a traditional way or a typical way that you would see a centrifugal pump behave. So as you see an increase in flow rate, you're going to see a difference in the head that the pump will produce. If you get a decrease in flow rate, you'll get an increase in head, and an increase in flow rate will give a decrease in head. If you change the speed of the pump, you'll see the performance change in accordance with the pump scaling laws. The efficiency of the pump will also be calculated because, or based on typical efficiencies for that size pump. The size of the pump is inferred through the volumetric flow rate, and that's then converted into an impeller diameter. So even though this says basic centrifugal pump, it actually has quite a lot of information stored within it, and the calculations that it performs are incredibly useful. So here we can even get a rough size of what the impeller diameter would be for that pump, along with what the expected efficiency would be. Okay, if we now, so now our system, we have a target CV value, we have a head for our pump. So we're pretty close to our specifications, but as engineers, we need to understand that the system may not always be at these perfect conditions. So we need to include some variance in our inputs and see how the system behaves there. So perhaps the level in this tank increases slightly. It maybe goes to 1.5 meters. We then see an increase in our flow over here. We need to then just account for that. If we look at this system over here, this pipe would be connected at the top. So, sorry, it's the incorrect specification. Okay, so any change in level here is going to increase the flow through here because there's an increased head of water above the outlet from this tank. So we see an increase in volume flow. Our pump itself is specified to only produce this value at this pressure drop, or this flow rate at the pressure drop. So maybe we should design our pump to be slightly larger. To do that, what we could do is just basically specify a higher flow rate, and then from there have the pump sort of operate in those conditions. So instead of the volume flow at best efficiency point being 10 cubic meters an hour, perhaps it's 11 or 12. Under its normal conditions, we then see our volumetric flow being higher. We also know that our valve over here is going to be completely limited. I started designing this valve with the valve completely open. So when this valve is fully open, we get a maximum flow of about 10 cubic meters an hour. Perhaps the level in the tank is too high and we need the tank to drain to regulate this level. We'd need to specify a higher CV. So instead of 7.2, perhaps we choose 8 as a CV. Now our valve over here can provide a pressure, can provide a flow of up to 11 cubic meters an hour. And our pump over here is also capable of producing additional volume flow. So we're then able to take our system, after we've built the network, got it solving, we can now start looking at some more of the analysis, some of the what ifs in the system, to make sure that we've thought of everything before we go ahead and propose the size of these components. So from here we could say a valve with a CV of approximately 8 and a pump with a head of approximately 20 meters, maybe 21 meters, at a volumetric flow of about 12 cubic meters an hour would be ideal for the system. All right, so if we go back to our presentation, I have a couple of other user input tips. I've mentioned a few of them while I was busy building the network, but we also have access to, I mentioned the tapping shift to rotate components. If you have a large network, perhaps this network extends across the page, it can be quite, I don't know, at least for me, quite frustrating to continuously grab the horizontal scroll bar and move. If I can use my mouse wheel to scroll up and down, you should also be able to use the mouse wheel to scroll left and right. You can do that by just holding in shift on your keyboard and then using the mouse wheel again. So if you're moving around networks trying to trace flow paths, it's very easy to do that by alternating holding shift and not holding shift to scroll horizontally and vertically. The next thing is you can use multi-selecting to do group editing. So let's say these two pipes over here had similar inputs. In this case, all the inputs are identical, but maybe we wanted to change the length of this to 15 meters. We can select both components and edit them together. This can be done for any number of components, and it only really works for components of the same type or components with inputs that are named exactly the same. So if a valve has an input called valve lift fraction opening and another valve has exactly the same name, then you'd be able to select the two components together and edit them in a group. But the rule of thumb typically is if the components are the same, you can edit them as a group. If you click on a component and you want to get to the inputs page, let's say that it was on the drawing page or you were working on some graphs, you can just press F4 on your keyboard. It'll jump to the inputs page for that component. And then if you're stuck and need more information about the component, maybe you're unsure what an input means or you'd like to know the theory behind the component, you can click on the component and press F1. What that's going to do is open the user manual for all the components and open it at the section where that component is discussed. So it's just a very useful way of getting to the exact point in the user manual that you need to be in. You can do this with a lot of other features. So you can do it with the menu items as well. If you'd like to know about the flow solver, click on that and press F1. You can do it for a lot of the items inside here. We already mentioned to type units with numbers. So as I did before, if the default value is say in meters and I want to specify a value in millimeters, all you need to do is just type the unit afterwards. And then lastly, it's also possible to put equations inside the input boxes. So maybe you're specifying the area for a component. This might be common on the restrictor with discharge coefficient. There's an option for this where you specify area, and you want to have this area calculated. You can actually put an equation in here, maybe 2 times 5, for example, and Flownex will then do the calculation for you. You have access to a lot of functions in there as well, and other variables. So you can use the variable pi, you can use the variable e. You have a lot of options. All of this is described in the user manual. If you go to the general user manual and go to section 2.12. So let me just open that quick. Here is the equation parser operations and functions. And you can see all of the variables that are available, all of the operations, the logical operations, and then all of the functions that you can use as well. Okay. When it comes to modeling larger networks, this sort of ties back to some of the thoughts we have before building a network, is only model what's necessary. Sometimes large networks can be incredibly daunting and can take a lot of time to build when the question that we're looking to answer really only lies in a small portion of that network. It's not necessary to model everything to answer that question. So always keep in mind, what is the engineering question that I'm trying to answer, and what do I really need to model to answer that question? If you have a large system with tanks, a pressure regulator, a large pipeline, and a tank that may be flashing, instead of modeling the system with the tanks and the pressure regulators upstream, you could simply just model that as a pressure boundary condition. Maybe you've tested the pressure regulator and the downstream pressure is fine, but you suspect that some valve may be operating incorrectly downstream of there. Modeling the upstream components isn't actually adding any value to your simulation. So try stick to what is strictly necessary when modeling these systems. It'll save you a lot of time. The next thing, I've touched on this with the example that I presented, build the network in stages. If you're modeling a cycle, what can often be very useful is to place a component down, put a boundary condition at the inlet, and a mass, like a pressure and temperature boundary at the inlet, and then at the outlet, put a mass flow boundary. So perhaps you're specifying a turbine component. You've changed all the inputs for it, and you're confident that it's good. You hit solve, and the results look acceptable. You then move the mass flow boundary condition down and add another component just downstream of that. Connect the mass flow boundary condition at the downstream node of the new component, and then repeat the process. So ultimately what you're doing is adding a component, solving, adding a component, solving, maybe adding a handful of components and then solving. The important thing is that you're continuously checking that your inputs are specified correctly, so that if you ever have to add the component again, you don't repeat any of your mistakes. And then lastly, when it comes to large networks, sometimes we make modifications to the inputs of components and we get solver errors that are very hard to find the root cause of. What I'd recommend doing there is disabling sections of your network. You can do this just by highlighting components and then unticking this box that says solving. what that'll do is remove these components from the flow solver calculations. They still exist on your drawing canvas, but the solver will treat them as if they didn't exist at all. And the components will be disregarded in the solution. So what it can really do is help you narrow down sections of your network that are existing or working, and at least help you narrow down which portion of your system the problem lies in. Okay, the next thing I'd like to talk about is some of the components we use most often. These are components that I see as relatively general purpose components that we can use in many different applications. What I'd like to do is just talk about a couple of them and say when we'd use one over another. What we've already used is the open container. This is a component that I like to use when modeling some sort of pressurized container with a level inside of it. If you have, say, a pressurized container with water and steam, it's not the component to use. In that case, I'd use a two-phase tank. That's ideal for modeling liquid and vapor phases in the same container. But if you have a container with, say, water and air above it, and the container is pressurized, use an open container. It has an option for free surface pressure, and it can get you out of modeling an entire air system. The next component that I'd use often is the reservoir. The name may be a little bit cryptic. The reservoir over here is a sealed tank. It doesn't have any openings to atmosphere or anything like that, but it can be very useful for modeling parts of systems where the volume of fluid is important. So perhaps you have a simple, like an HVAC simulation, and you're trying to simulate the flow into a room. The air inside of that room has quite a significant volume, and in a transient simulation, that volume can have a large effect on your results. So modeling that volume with a reservoir would be an ideal way of capturing that inertia. All of the accumulation terms would basically capture that effect. The next section I'd like to talk about are generic pressure drop components. So here we have three different options that I tend to use. We have a flow resistance component, a general empirical relationship component, and then a user-specified pressure drop. These are all used when you don't have a geometric representation for the component. So it's not a duct with a hydraulic diameter or an area or something like that. It is the flow of air around a heat exchanger, for example, or perhaps a filter in the pipeline, something that defining the geometry for in the flow path isn't very easy. So instead, I would attach one of these components and then use some experimental or some plant data to characterize the pressure drop over this component so that it represents the pressure drop that you would see in reality. If you have only a single point of data where you know the pressure drop at a single flow rate, then I'd recommend using the flow resistance component. It has an input called admittance, which you can vary, and that will change the pressure drop over that component. You can also change how you would like this component to scale with the volumetric flow. It can either scale quadratically, linearly, or with a square root relationship. And you can also enable or disable density scaling as well. The next component is the general empirical component, or general empirical relationship. This component I use when we have multiple points of data for pressure versus flow rates. So in this scenario, we may want to characterize what the effect of density and volumetric flow is on our pressure drop, but we don't want to stick to just linear or quadratic relationships. We may have density to the power of 1.3 and volumetric flow to the power of 3.2, for example. These wouldn't be possible with the flow resistance component, but the general empirical relationship allows you to vary those exponents. So we can vary a coefficient similar to like a secondary loss coefficient to scale the pressure drop, but then also vary the exponents for density and volumetric flow to account for how the pressure drop varies with these variables. What I often use is a small spreadsheet that I've built that calculates or does the regression calculation for this. The formulation for this pressure drop you can find in the user manual, and you can basically just in a simple Excel spreadsheet calculate what the coefficients and exponents need to be to match your experimental data as close as possible. You basically do a least squares regression through your experimental data, and you can get the ideal values for CK, alpha, and beta. The last case is when you have experimental data for a component for a pressure drop, and you want Flownex to use exactly those values. You don't want to characterize a pressure drop and work out what the coefficients for your traditional pressure drop formula should be. You actually just want Flownex to interpolate those pressure drop values based on whatever the volumetric flow is through the component. So this last one is basically a lookup table for pressure drop versus flow rate that you provide Flownex. So this is useful when a component has been rigorously characterized with experimental data. We see this in the automotive industry quite often, where manufacturers might characterize the pressure drop through a radiator or a condenser, for example, and they'll do it at multiple different flow rates. We can then use that information to specify the exact pressure drop and use the user-specified pressure drop components to ensure that the pressure drop applied in Flownex matches the experimental data. Okay, these are more general components. When it comes to any 1D flow with a known geometry, so by known geometry, I mean a known diameter or a known flow area, something where we can actually calculate a velocity in the component. In that scenario, I'd suggest using the pipe component. In Flownex, you'll see there are other components like a basic pipe and a mine ventilation duct, and let me see, there's another and a insulated pipe. These components can be useful, but we tend to rely on the pipe component for almost all of our 1D flow cases, or 1D flow cases with geometry. So the pipe component has a relatively small list of inputs. You just need to specify length, diameter, roughness, and then you can add secondary losses as well if you'd like. You don't have to specify the advanced inputs, but if you would like to, there's a little tick box at the bottom. This then gives you access to additional inputs like heat transfer from the components or specifying restraint options for water hammer studies. So when this is not ticked, you have very few inputs over here. So using the pipe component can be a very ideal way of modeling these one-dimensional flows with geometry. For our heat transfer applications, the composite heat transfer component is almost always my go-to component. It has features that can model just about any form of heat transfer. So if you're modeling, say, heat losses in pipes or tanks, or maybe you're trying to do a more sophisticated heat transfer model where you're modeling a heat exchanger that's been discretized, perhaps it's a steam generator for a power station or a tube-and-tube heat exchanger. All of this can be modeled using the composite heat transfer component. I find that it's most useful when modeling convection, conduction, and convection again. So for example, heat transfer from the inside of a pipe through the pipe wall. You can account for different conduction layers. So you could account for the effects of fouling by using this component very easily. And then account for the convection on the outside of the pipe, be that into another fluid or into ambient conditions. This component is very easy. The nice thing about it is that it will automatically match the discretization of the pipe component that it's connected to. So with the other heat transfer components, you'd have to drag and drop components and build your discretization manually. The composite heat transfer automatically follows the discretization of the pipe. So in terms of time spent dragging and dropping, this component really saves you a lot of effort there. When it comes to pumps, I already mentioned the basic centrifugal pump is my go-to for pump sizing. It's really ideal for that, or in a case where you have a rough idea of pump performance but no pump chart, then I would say the basic centrifugal is a good go-to. The variable speed pump is good for scenarios where you do have a pump curve. It allows you to specify multiple pump curves at different speeds, but if you only have one pump curve at one speed, the component will work just fine at that particular speed. Often with pumps, I'll use the shaft component as well to add inertia to the pump. The variable speed pump and basic centrifugal pump don't have inertia built into them inherently. To account for the inertia, you have to connect a shaft component. This is useful for doing startup or shutdown simulations. Perhaps there's a pump trip or a pump startup that you want to investigate. And the shaft component is also useful for connecting pumps to turbines in cases where you have a turbo-driven pump or a turbine driving a compressor, for example. In terms of compressors and turbines, the positive displacement compressor is ideal for modeling screw and reciprocating compressors. Or even in a case when you don't have a compressor chart, but you have a rough idea as to what the flow through your compressor needs to be. This component's not bad. It won't scale in the same way that a centrifugal compressor will, but you can account for the efficiency of the compressor, and you will see that effect in the temperature results from your or temperature of the pump outlet. When you do have a compressor chart available, the compressor component is the best to use. This is going to give you the most accurate results. All of the inputs are non-dimensionalized and scale very well. When it comes to modeling turbines, a simple turbine is really good when you don't have a turbine chart. Perhaps you're doing a cycle analysis and you're trying to understand the efficiency changes in a cycle when you add and remove components. Perhaps you're studying a Rankine cycle and you want to consider reheating or not consider reheating. You don't really want to model the turbines with full turbine maps. It's just better sometimes to use turbines with a known pressure ratio and a design mass flow rate. In that case, the simple turbine is the ideal component to use there. When you do have a turbine chart, so if you're in like detailed design or if you have a plant that's already operational and you're able to get charts from the manufacturers characterizing the performance of the turbines, then using those turbine charts with the turbine component will produce more accurate results. All right, and lastly, we have a couple valves. The basic valve itself is the most simple valve model. This assumes a linear change in CV from 0 opening to full opening. It's probably the easiest valve to use. It'll work well for valve sizings for incompressible flows. If you're looking to account for choking effects or model compressible flows better, then I'd suggest the ANSI control valve. It's going to be more accurate for compressible flow. It also does choking a lot better. You can model different types of valve curves. So you can model an equal percentage curve, a linear curve. You can even specify an ANSI chart to capture the exact performance of your valve. Lastly, you can use a control valve with loss coefficients if you'd actually like to take a manufacturer's valve curve and import that directly into Flownex. So if you're going through a catalog and trying to choose a particular valve and the manufacturer is kind enough to supply the valve curves, then this component would be ideal for inputting that curve in and using that in your simulation. You might have noticed earlier in the simulation, I took a ball valve from the Miller section of the valves library. These are general purpose valves. They're like a rough characterization of the typical behavior of these components. So they're not going to be as accurate as if you had the actual valve curve, but they're better than just assuming a linear valve curve or an equal percentage valve curve. So if you're doing a control study and you're being really particular about the dynamics of your valve, then I'd suggest using one of these, if not changing to the control valve with loss coefficient. Okay, lastly, I'd like to talk about time steps and increment selection. So on the pipe components, you'll notice that there is an input for the number of increments. This is the spatial discretization of the components. It basically takes a pipe component and slices it into multiple pipes, all connected in series. We can then have this pipe solved with all of its individual pipes accounted for, basically allowing for more accurate modeling of the fluid properties as they change along the length of the pipe. So this really only becomes significant when we see a large variation along the length. So for example, if you're modeling a heat exchanger, the change in temperature is going to change the fluid properties considerably over the length of the pipe. So including increments there is essential. If you're modeling a pressure pulse in a system, perhaps it's water hammer, you're going to have the pressure along the length of the pipe changing rapidly. This is very important, or in this case, it's very important to consider the spatial discretization of the component, so the number of increments that you select. As for how many increments you should use, that really depends on the application. The most general advice is that you should test for mesh independence, basically refine that mesh until you don't see any change in your results. A good technique for this is described by the author Roche. If you Google this name, you should be able to find a particular paper. He refers to Richardson extrapolation to find the 0 increment length result, and then define something called a grid convergence index, which helps you decide at what point your mesh is sufficiently refined. If you're struggling to find this paper, just let me know. I can help you find the links. Okay, and then the last thing is time step selection. So in Flownex, we might be modeling very different processes. There might be a slow process like ambient heating of a tank over many days. You might be modeling a concentrated solar plant where you have changes in solar or your solar flux over the day, and you want to study what effect this has on the performance of your cycle. So modeling this with very small time steps would be quite impractical. Flownex has an implicit solver, so we can ensure conservation of all of our primary variables. So we basically ensure our conservation of mass, energy, and momentum. And we can then take larger time steps in these scenarios because we're not seeing very big changes in our system conditions across time. We may be able to take time steps of a second, maybe upwards of that. In some really slow processes, we could take time steps in the order of minutes or hours. For more standard processes, say you're doing an investigation of a pump trip, or perhaps there is a control study with the level in a tank or something like that. For that, I'd recommend time steps of about 100 milliseconds. That's the default value in Flownex, and that should get you by most of the time. And then lastly, when you're considering studies like Waterhammer and other similar very fast transients, you're going to be looking at time steps in the order of about 10 milliseconds, sometimes even smaller than that. There are cases in short pipelines where 1 millisecond time steps are required. One of the best ways to characterize whether your time step is small enough or not is to consider the CFL number. Some people call it the current number. This value is actually calculated inside of Flownex on all of the pipe components. If you click on a pipe and look at the results, you'll see the current number for momentum and for scalar transport. The momentum transport considers the current number with the speed of sound inside of the fluid, and the scalar transport considers the current number with the velocity of the fluid. So both of those can be a good indication as to whether your time steps are small enough or not. You can also go to the solver results. If you click on Flow Solver and go to results there, you'll see the maximum current number for momentum and for scalar transport across your entire simulation. So you don't have to check it pipe for pipe. There is a section in the code that actually takes the maximum value and reports it over here. So you can use this in refining your time steps, particularly for fast transients. Anything smaller than a CFL of 1 should give you good results. There are some special cases where you need to go smaller than that, but if you're working on that and would like some more information, please feel free to contact me. I've done a lot of work in these fast transients and can give you quite a bit of advice regarding how small your time step needs to be to capture particular phenomena in these fast transients. Okay, we're just about out of time, so I'd like to do a quick summary. One thing that I really like to stress is plan your simulations carefully. There's a quote by Abraham Lincoln. He says, if I had 9 hours to chop down a tree, I'd spend the first 6 sharpening my axe. So considering all of the inputs in your system and thinking through all of that is going to save you a lot of time in the long run. Modeling only what's necessary. So considering what engineering questions you would like to answer, and then from there, make decisions about exactly how you should model the system, exactly which portion of the network is important to model. And then also choose components relevant to the level of detail that you require. So if you're modeling a basic power cycle just to analyze the efficiency with changes in the cycle design, don't go ahead and specify complex compressors using compressor charts. It's going to waste a lot of time. Modeling the compressors in a simpler fashion would save you a lot of time and get you similar results. So choose your component, the level of detail in your components carefully. Don't just always resort for the component that's name seems to match as best as possible. And then lastly, if you get stuck, please reach out to us. We're happy to support you. We have resellers all around the globe as well who are more than happy to help you out. We basically like solving difficult problems. So if you get stuck with something, please let us know. We're happy to talk you through it. We've got a lot of engineers that have been working on the software for a long time. So we can give you advice on particular problems, propose modifications to your solutions, or basically help you through some of the common challenges in modeling particular systems.